I will turn it over to our presenter, Dan Tekiela.
Thank you, Belle, and thank you all for attending this webinar. I imagine everybody's kind of webinared and zoomed out, so I appreciate all your time and willingness to spend some time with me on this topic. So I think it was really great that Belle gave a little bit of a background of my experiences, because I think it meshes nicely with kind of a rationale as to why I take an interest in this topic of remote sensing. So as she mentioned, these are the 3 institutions that I've been associated with, and throughout these different institutions, I've worked in very different systems. So working in Illinois, it was much more prairie type systems. Moving to Virginia was much more of eastern deciduous forest type systems, and now at University of Wyoming, much more of a rangeland open type systems. And even though there's a variety of differences in the approaches and techniques and strategies and all these different types of ecosystems that we manage invasive species in, the one thing that always kind of came back to me was being able to detect these things early on, right? Early detection, rapid response is something that hopefully everybody who's attending has some familiarity with. And it's just the idea that you respond, or first you identify new invasion as soon as possible, and then you respond to it as quickly as possible. And obviously, to be able to do this, we have to have good strategies to actually find invasive species on the landscape. And this is actually quite difficult to do. So now that I'm here at University of Wyoming, I've been spending a lot of time trying to further our understanding of how to potentially leverage and utilize remote sensing technologies to better detect invasion. So I would be remiss not to mention that now that I'm working with a group of students, that a lot of this actual work, the science going on, is not being done by me. It's being done by one of my students, Chloe Matilio. So this is a cover from our local extension publication showing her during a field tour where she was showing some of the technologies and strategies we're trying to utilize for invasive plants, for us in particular, detection. And I just wanted to give thanks to her for all the hard work she's been doing on this topic. Okay, so as opposed to giving an outline, I figured the way to approach this was to kind of pose a couple questions. And my goal by the end of this presentation is that you all can answer these questions based on what we present today. So first question being, what is remote sensing? And this is actually kind of an important question that we might take for granted. I think we tend to pigeonhole remote sensing into very particular things that are done in remote sensing, but it's actually quite a broad topic and technology that I think we can leverage. Next is, what information can we remotely collect? And frankly, should we be collecting if we're interested in identifying invasive species? How do we collect that remote sensing data? Basically, what are the platforms that we can use? And then how can we use the information that we remotely collect? How can we get something out of that that's worthy and helpful from a management perspective? Okay, so to not waste any time, we'll get right into it. So what is remote sensing? So I would argue that we've been remote sensing basically since we have been a species. And as Chuck Norris has kindly lended his gaze at us for, our eyes are some very sophisticated remote sensors. So the fact that we can detect some type of information at a distance without directly contacting it, that is inherently remote sensing, right? Now, if we talk about it from kind of a scientific or a management perspective, I don't think most people would consider this remote sensing. And the reason being is that when we remote sense with our eyes, we don't have a good method of storing that information long-term, right? Our brains are very fallible. They don't remember that detail of information from a particular image, and therefore we can have a lot of error associated with that, especially the longer and longer that that information is stored. So if we kind of ramp up then technologically the next step, well, I would argue that remote sensing first occurred then when we took the first photograph. So this is an image of one of the first mass-produced cameras, and I don't know exactly the camera that was used, but the first image taken is believed to be in 1825. So we've had hundreds of years of taking photographs, and frankly, that is remote sensing. You are collecting information from afar with some piece of technology and storing it, in this case, a photograph, long term. Now, obviously, this has evolved if we just talk about cameras as remote sensors, and now we have really sophisticated, high resolution, high definition sensors such as that found in a DSLR camera that allows us to digitize this information. So really, remote sensing is just collecting information from afar. When we talk about it in the kind of scientific and management world, it's doing so and having some type of stored information that we can then leverage to make better decisions. Okay, so what information should we remotely collect? So we've already kind of spoken of what I think is probably the most important one and what we'll spend the most time on, and that is light. So light information is one thing that is potentially useful to remotely collect. And I'm also grouping light with heat, and you'll see why in a minute here. But these two I'm representing with the sun here because these are forms of what I'm going to refer to as passive remote sensing. And really what that means, as I'm showing here on the right with this figure, is that we are not actively sending energy out to do that remote sensing. We're depending on some other source of energy that we are then collecting information about. So in the case of light, we have the sun that is emitting some source of energy, and then it's being reflected by an object that we care about, and we are then collecting that information with our sensor, whether it be a camera, or we'll talk about some other options later on. Heat is a very similar thing. Heat in some cases isn't necessarily reflecting. It could be such as an animal that can create heat itself. But again, we are passively measuring and detecting that heat. We are not emitting anything to do so. So it's important because it's contrasting what would be active remote sensing. So I'm representing active remote sensing with a laser beam because in these cases, we use an emitted source of energy, right? We don't shoot laser beams out of our eyes, but we can shoot a laser beam out of some sensor, and then based on things like how long it takes for that to reflect off an object and get back, can measure something like distance. And that is, I probably would say, the most important piece of information that we can remotely collect with an active sensor is distance. And we'll talk about how that may relate to invasion. But we're going to spend most of our time on passive sensing because I think this is where, frankly, there's the most information right now and where I think we can get the most use out of remote sensing technologies. Okay, so if we stick onto this topic of light and how we can potentially use light, I'm going to try to keep figures to a minimum, but I think this is a relatively simple figure that really gets at the point of how we would leverage and use this information. So I've got a spectrum on the bottom here of visible light, and it's kind of being mapped onto this figure. And what this figure is showing is the different bands of light, right? So there's bands of blue light and bands of green light and bands of red light, and those are being highlighted by these gray areas here. And we can actually map how much reflection occurs for different objects in these different bands of light. So for example, and this is somewhat of a characterization, but it does represent, generally speaking, what we would see. If we look at something like water, as this blue line here, we're going to see more reflection occurring, thus this hump in the middle around the blue and green light. And that's why we're going to see that color water that we typically see. If we contrast that with something like our bare soil here, we're going to see, generally speaking, and again, this is going to be proportionally, that we have more red light being reflected than we do blue light. So these reds and yellows are why we see the bare earth as browns and reds and those kind of darker colors. And then we've got vegetation, and this is just generally and broadly speaking vegetation, so not any particular species. But in that case, just looking generally, we see somewhat of a hump in this green and blue area, and then this kind of odd, very sudden, abrupt increase over red, which might not make sense because we don't see vegetation typically as red, but we'll talk about why that is in a second. But theoretically, if we can see that these different reflection bands are different between our bare ground, our vegetation, and our water, we can separate these things out, right? And that's what our goal is to say, can we separate out bare ground from vegetation? If we can't even do that, then we certainly aren't going to get down to a species level where we start to actually use these technologies for detecting a species. But we certainly can separate out something like bare soil from vegetation. But on the note of can we separate out one species from another, we can actually go one further, and this is a figure, and on my apologies, it's a little bit grainy here, but it's looking at a sweet gum leaf. So it's an eastern deciduous forest tree, and it's showing the different reflectance. So again, this is exactly like we were looking at before. We have reflectance, so the higher or the taller the bar, the more it's reflecting. and we're looking over visual light, and we can actually separate out something like a green sweet gum leaf from a red or a brown one as that plant starts to senesce. And we can tell that we can see the difference because these lines are different, right? So those differences in those lines can potentially be used by us or by a computer to detect that those are two different stages of life for that particular leaf. So certainly giving some potential suggestion that we could separate out individual species on a landscape for detection of an invasive species. Okay, well, we're gonna go back to Chuck Norris here, and he's gonna be our kind of representative of what we're able to see. So this is visible light, right? I already showed it to you going from blue to red. This is what we can see. However, this is just a small portion of a much larger spectrum of energy. So really all light is it's a portion of the electromagnetic spectrum. And this is the full spectrum. So to give you a sense of this is all that we can see over this entire range of energy. And you might be familiar with some of these names. You know, infrared, we think of like heat, microwaves, you know, microwave your TV dinner, radio waves sending out information. These are all the exact same thing. It's just our eyes are only able to see energy in this particular wavelength. So why might that be important? Well, if we're only collecting this information, whether it be with our eyes or like we've been talking about a camera, we're missing out on a lot of other information that might be useful to detect different species. So to give you an extreme example that's not necessarily related to invasion, this is looking at a particular species of bird, and I don't even know what species this is. I'm a plant person. However, if we were to try to detect this and describe this, I would describe it as probably a black bird with some very nice yellow accents, and maybe that's how we would try to pick out this bird from other species, is these yellow accents, but overall pretty muted species. Now, to remind us, that's within our visual range, right? So from blue to red, that's what we are seeing. Now, if we compare that to something like what a bird would see if they were looking at that exact same bird, it would be a very different story. So this bird looking at the exact same image would see these very contrasting colors on this bird. So if you're going to try to detect this image over here from this image over here, which one would be easier and look more unique? Well, it'd be the one over here, and that's because this bird is able to see more in this ultraviolet range that we're not able to see. So if we could collect information in other parts of that electromagnetic spectrum, that could be really useful for us as we're trying to differentiate one species from another. So we actually have the ability to do that, and we have sensors that are able to do this. And the terminology that we typically use is either multispectral or hyperspectral sensors, and they can come in a wide variety of parts of the electromagnetic spectrum that they see, how fine of resolution between one band and another that they can see. But overall, we have the ability to do this. So let's bring it back to my world in plants and why that might be important. So if we go back to this figure here, you know, yes, we certainly see differences between vegetation and water and bare soil. But if we then look further on into that electromagnetic spectrum, we see a whole new story, right? And a very interesting story. They're very different now. You know, the soil has this kind of increasing shape. The water doesn't reflect at all or much at all beyond our visual range. But if we look at vegetation, there's all these unique valleys and hills in reflection that's occurring in parts of that spectrum that we can't see. That could be really important information to look from one species to another. You know, the small changes that can occur in these valleys and these hills might be able to differentiate one species from another. Okay, so I mentioned that we were going to talk about heat in the context of light, and hopefully you're kind of understanding why that is now. So this is an infrared image. It would come from something like, you might be familiar with a FLIR camera. And, you know, we can see that the cow here is emitting much more energy, in this case, heat energy, than anything else around it, and therefore it sticks out pretty brightly. I do know that in the recent past, there's been ranchers and farmers that are starting to utilize this type of technology that can see heat, infrared energy, to track where livestock is on the landscape, right? Because if you're able to use these bands, this animal is going to stick out a lot more against the backdrop of rangeland in my case, or pasture in some other area, than trying to pick out a black spot in a sea of green. So this is something used by ranchers, but we're actually seeing it starting to be used in the invasive species world. If you think of things like wild boar or goat culling, from an invasion standpoint, they might be using infrared cameras to more easily detect either those boar or those goats on the landscape. But why I'm kind of clumping this in together is because it isn't technically different than our light information. It's just a different part of that electromagnetic spectrum using a sensor that's able to detect that. Okay, so that's kind of generally the type of information we would collect passively, but what about actively? So like I mentioned, this is going to be distance information, and I think the best way to stick this in your mind is to look at a kind of a neat example that we can all probably find a connection to, and that's the missions to the moon. So in the Apollo missions, one of the things that was left by a couple times were these reflector panels, and this is an image of one of those reflector panels, but they actually have a really neat design where if you emit any energy at them, they reflect it directly back, no matter the angle. So what we can do is we can shoot a really powerful laser at one of these panels, and based on how long it takes for that energy to hit that panel and come back to the sensor, we can measure a time and we can translate that to a distance. So how is that related to the world of animal and plant invasion management? Well, just like we would in LiDAR here, this is a topographical map. I hope we're all familiar with topographical maps. This would be created by this LiDAR, or the ability to emit some type of energy and reflect it back up to that sensor. That's how most of our more recent topographical maps are created. So how can we use this in invasion? Well, one example that I have of it being a piece of information that could be useful is a study that was looking at invaded and non-invaded forest systems. And I don't want you to kind of focus on the minutia, but if you look between these dashed lines here, on the left is the invaded forest, on the right is native. And in some cases, you see just visually a structural change after the invasion. You can measure these heights, right? If you can measure a distance and you know a couple different distances, you can measure a height, and therefore you can translate that to how tall is the vegetation in this case. And that could be a piece of information that helps you determine if it is one species over another, is the height information. Okay, so how do we collect remote sensing data then? So we know what it is, we know what type of information is most useful, so what do we do? So I would say historically, one of the first kind of strategies used for remote sensing information was utilizing planes and helicopters, right? So we'll talk more about these in detail, but going up into the air to get a better view. Kind of next in line and commonness of use has been satellites. So once satellites became more common and imagery technology was better, we're starting to use satellites for being able to detect invasion on the landscape. And then most recently, and my guess is what most people think of now when they think of remote sensing, is unmanned aerial systems, or UASs. I represent that here with a quadcopter. It doesn't have to be a quadcopter. It can be a fixed wing. It's just anything that doesn't have a human inside of it controlling it. They tend to be smaller platforms because they don't need to also carry a human within them. So we're going to kind of talk about all three of these, but one thing I really want to clarify is that we're not going to be tackling regulations. In particular, this is relevant for unmanned aerial systems because they're variable, and I am not the expert in that. So I just want to put a caveat in there that we're going to talk about it as a technology that could be useful, but you certainly, if you have any interest in any of this, need to ensure that you're following regulations once you get into airspace. Okay, so in terms of planes and helicopters and how they might be useful, I think it's kind of cool to think historically how we first started to use planes or helicopters in invasive species management. And I know here in Wyoming, there's a couple examples of counties that would basically go up with a pilot and a weed manager or an invasive plant manager, and they'd go up with a map and they would fly around and just manually draw polygons on those maps as they went that generally represented where they thought it was on the landscape from what they were seeing from this bird's eye view. I mentioned it already when we were talking about the infrared imagery, but planes and helicopters are being used in both the management and the detection of different mammals. So like I mentioned, wild boar, where they're potentially using sensors on these aircraft to more easily find these animals, and then also potentially calling the animals at the same time. Satellites are becoming more and more prevalent in their utilization for invasive species management, and particularly in plants, because plants don't move as much, or at all, at least individually. Partly because the sensors are becoming better and better, but also because if we look at the current map of satellites that we have orbiting the Earth, it is just immense, and the opportunity to collect information increases every single time we put a new satellite in orbit. So this kind of gives you a representation of the potential set. I'm not saying all of these are collecting imagery data, but this just kind of shows that there's a lot of potential there. So much so that if we think about something like Google Maps and the utilization of satellite imagery, I'm pretty sure most of you, if not all of you, have probably been on either Google Maps or some other mapping platform where they have what they will refer to as satellite imagery. And that's because it's literally coming from a satellite. This in itself, looking at this image in the bottom left, could be used for potentially detecting something if it was large enough scale. If you've zoomed in, I can zoom in on this image of Laramie where I'm at and potentially look at the roof of my house. Well, if I'm looking for maybe a shrub or a tree species, that might be a reasonable way to try to find something. Okay, and then the most recent platform that I mentioned, unmanned aerial systems, just to remind us that they aren't all quadcopters, because I think that's what we always have in our heads. This is an image of a project that we were doing where they were using a fixed wing aircraft instead, but it all boils down to having some type of a sensor or camera or something on one of these platforms. Obviously, this has become more and more popular in very recent past because the prices of these has just dropped precipitously. And just for the fun of it, I went on Amazon and looked up what the cost of any of these would be. And this is not to suggest that these are going to be professional grade drones or quadcopters that you're going to potentially use as an unmanned aerial system. But it does show that the price of them has just absolutely dropped to reasonable prices where anybody could at least try it. So these are kind of our three platforms, and I want to give you a kind of a brief comparison of where I think there's kind of the pros and cons of them. So for satellite, kind of our largest scale imagery, because they are so far from the Earth, they have really large coverage, right? They, in a single image, can cover a huge amount of area, and that coverage is going to be consistent. It's literally flying in orbit. It has to be highly precisely controlled. Therefore, that coverage is going to be very consistent. However, because it is such large coverage and it is so far away from the Earth, the scale is going to be really coarse. And we'll talk a little bit about resolution, but it's going to be really hard to get fine scale pictures where you can maybe pick out one plant or one animal from another one. They're not controllable unless you happen to be a millionaire or Elon Musk or something. You're not able to direct where they're going or when they're going to be somewhere. So you have to seek out already existing information or flight paths that are already planned to try to get imagery. And obstructions are a major issue. So this is a great kind of representation of that. We have lots of clouds on the Earth, right? And if you happen to have an image taken on an area that there was a cloud at that time, depending on what information you're trying to collect, that cloud could completely cover it and make that image not very helpful. So if we kind of go down to the next finer scale of planes, well, they are finer scale. Literally, they're closer to the Earth. Therefore, if you're trying to collect actual imagery from them, it's going to be easier. Or sorry, it's not going to be easier. It's going to be finer scale. Fewer obstructions. You can fly under clouds. You can fly around things. So you could argue that there's very few obstructions. They can be real time. So you can schedule with a particular pilot, and if you want to have imagery at a specific day or a specific hour, you can make that happen. But some of the downsides of them are that there's more variable coverage. So Flight paths are going to be a little bit looser. Elevation adjustments are going to be looser, and therefore there's potential for error there. Human error associated with that flight path, right? That you're depending on the pilot to keep that straight line. And they can be costly, right? If you have a great friend who's a pilot, maybe you can find a good price for this, but generally speaking, having a flight dedicated to collecting information is going to be relatively costly. And then if we go to our finest scale with our UASs, they're very fine scale, right? We can fly very close to the ground, and in fact, we can't fly very high. There's regulations associated with flying too high, so that brings us into a very, very fine scale data collection that we can do. It's fully schedulable. I mean, you can be the one that manages all of that and goes out when you think it is warranted. You don't have to have a pilot or something associated with that data collection. They're generally inexpensive, like we just covered on the previous slide, but they are very limited in their area covered, especially if you're looking at a quadcopter, which most people seem most interested in. They're very limited in the total area they can cover by battery technologies and just the size of the platform. And they're new technology, and there's going to be potential oddities associated with that where things just go wrong, or at least that's our experience with them. Okay, so this is where we're going to spend a lot of time, because I think this is what people think of when they think of remote sensing, and that's how can we use the information we remotely collect? So I'm going to go back to really simple first, and we're going to kind of work our way up into more complex strategies. And I don't mean to be condescending in any way, but I would argue that kind of hearkening back to my Chuck Norris joke, that real-time analysis can be very important. So this is an image or a painting of a rancher back in the day on a high point in the landscape, overlooking his land. And maybe in that case, he was looking for weeds or other issues on his landscape. And I would argue that this is an important potential strategy for remote sensing that I don't think we should take for granted. But it has kind of moved into the 21st century, and we have other ways to do this in a much more efficient way. And I want to give you an example of that. This is an example of kind of the modern cowboy on his horse, in that this is going to give you an aerial perspective without ever having to leave the ground. So what we're showing here is this sweet rig he's got on his head is basically an image that's going to be live sent to him from a drone or an unmanned aerial system that he is controlling. And on the right here, we're going to play a video showing what he would be looking at. So anybody familiar with the Western US knows the species cheatgrass, and what we're looking at here is a cheatgrass invasion. And you can see that this is actually a southern slope on this left side of the image. And where cheatgrass is, there's some purpling, and that's really common for cheatgrass. Now, because he has this UAS where he can fly really high, he can get up off the ground and look at where that cheatgrass contour exactly exists. And even if, let's say, he wasn't looking for a large scale invasion like this, but there was a particular species, there would be nothing stopping him from real time flying down really close to the vegetation and trying to pick out an individual plant. It would save lots of time in that this person doesn't then have to go out and trek across that entire landscape. And if you think, especially at least here in Wyoming, where we have some relatively rugged terrain, where trying to get a person up on a mountainside where we might have an invasion occurring, you no longer have to send a person up there. You can have a UAS that person controls real time and says, "Oop, I found something," and then you can send people out in a more efficient manner. So that's kind of the simplest form. I mean, technologically, it's really incredible, but there's no back-end data collection, right? We're not storing any information. It's just kind of like an extra set of really sophisticated eyes. So if we kind of go to the next step, where we're actually going to use the information, we're going to collect it and then process it afterhand, it's best that we no longer use a manual flight and we instead use controlled flights, right? So with satellites, those flights are controlled by the orbit. Well, if we're using something like a UAS, we can control a flight path that gives us really good imagery. So I've got two examples here. On the left is from a program called Drone Deploy, and then on the right is from Pix4D, and it just escaped me, Pix4D's version of this. And both of these are flight planning softwares. So we'll focus on the left one here. Basically, the idea is that you drop a polygon down where you have interest in collecting information, and then the computer or your cell phone in a lot of cases will automatically develop a flight path for that UAS that will give you the best imagery based on your parameters. So in this case, what we're looking at is a flight that's halfway in process, where the blue line is what was created by the software for the flight path, and then the white line is the actual flight path. So you as the pilot don't really do much other than maybe lift off the ground, and then it automatically does this flight path. And you can see the white line is the actual path, and it stays very, very close to that original desired path. So what that means is you get really consistent imagery. Same thing over here with Pix4D. Okay, so now you take a bunch of these images that are really precisely taken, and now what do you do with them? So, I manually took a couple pictures from a project that we had done and just kind of generally aligned them together. Nothing perfect going on there, but this would be what you would be doing if you were trying to do this manually, is looking at each image and try to, manually adjust it around. This isn't really going to give you a good product that you can work with. So what we do is what's a process called mosaicing. So we put these into a computer program that uses a bunch of very fancy algorithms to find where each image is aligned with each other image, and creates, in the end, an overall image of your site area of interest. So it takes all these individual images and creates one image. And what's really important is not only does it align the edges of an image, but it also does things like color correction, because as a reminder, we're not emitting energy to do this, we're depending on the sun. Well, the sun is variable in its radiance, right? We can have clouds that might maybe cover overhead, or well, that's kind of the main one, is clouds. We can somewhat correct for that by mosaicing and having the computer adjust our color based on each image. Okay, so now if we do that, we have this big image of our area of interest that we want to find or detect invasive species. So what do we do with it? Well, again, I think most people are immediately thinking of how computers can do this, but I think even at this step, humans can potentially play an important role. So imagine that you're given this image, or this is your area of interest, and you are interested in, let's say, white top. So it's a little white flowering plant. So it has these unique white flowers that we can potentially pick out with our eye, and therefore I'm going to have my technician go in to this image, and this is far finer resolution than this overall image suggests. Maybe I can zoom in on certain areas of this image and confirm with just my human eye and my experience whether that is actually white top or not, and I can make note of where that tends to be or happens to be. So this is a realistic approach, and this is called supervised imagery. So the supervised part just means that a computer's not doing it. You take that overall image and you're having a human, the supervisor, kind of do that detection work. So what are the limitations of this? Well, one, it's super time consuming. This is a relatively small area that I'm looking at here, but imagine if you're working with tens, maybe hundreds, thousands, tens of thousands of acres, the ability to have somebody go in and manually move around that image and look for a particular species. It's possible, but I would be concerned that even with the unlimited cups of coffee, eventually they're going to give out on that process. And what's going to happen is the second thing down here, more human error. The more tired that person gets, the more boring it becomes to just be staring at a computer all day long, the more potential for them to miss individual plants or whatever you're looking for on the landscape. And therefore the whole process and reason of doing this kind of falls apart. So it can be useful, but we have to realize that there are some limitations if we're going to depend on the human eye. Okay, so if we're not going to depend on the human eye, then the next step is what I think everybody thinks of when they think of remote sensing, and that is we take that same image from before, we do a bunch of magical computer stuff to it, and it spits out something like this and says, hey, that's where we think that your invasion is. And this is kind of the pie in the sky. This is what my group is working on trying to do, where you can have the computer determine where the plant is, or at least give you a probability of, hey, there's a high chance that our invader, it doesn't have to be a plant, but we're working with plants where we think it might be. We're not going to get into the details of how this is done, because this is a sophisticated statistical modeling using machine learning and other techniques that are, I think, beyond the end user being able to use. But the hope is that people such as my group and others can start to make this an easier process where it doesn't take, you know, almost supercomputers to be able to do this in a timely manner. But I want to give you a sense of how a computer might do this, and also kind of go back to that topic of looking at parts of the electromagnetic spectrum that we can't see with our eye. So this is looking at Dalmatian toadflax, which is it's a perennial forb invader that we deal with a lot in Wyoming and many other Western states. And this is a real color image. So this is, you know, taken from the standard camera that you and I would think about. And what we see here is most of the green is Dalmatian toadflax. So there's some other things in there. And then these little yellow flowers are Dalmatian toadflax flowers. So we could potentially use that in this real color image to pick them out, but it actually is quite difficult with this real color image. What we could do is separate out things into different bands of color. Remember, we showed that you have different bands of reflectance that you can look at. So what we're doing here is we're looking at just the red band and just the near infrared band. So red we can see. And if we look at the red, anything that's light colored here is reflecting more red. Anything that's dark colored is reflecting less red. And what we see is that those little yellow flowers are really kind of stark and stand out a lot in this red image because they're reflecting more red than anything else around them. I think what's more interesting though is we go into near infrared. So this is part of the electromagnetic spectrum that we cannot see, but a sensor can. And in this case, we used a multispectral sensor, and the vegetation really pops, right? It stands out more than it does in this real color image. So why can't we use a combination of seeing this vegetation that really stands out here with the little yellow flowers here and tell the computer these are important things for it to potentially be Dalmatian toadflax, and then have the computer crunch the numbers and spit that image out. So this is really what computers are doing in a very sophisticated way. But I would also want you all to think about this as something where we can visualize other parts of that spectrum and how they might be useful in terms of detecting particular species such as Dalmatian toadflax and its unique reflectance in near infrared. Okay, so some important considerations if you're going to try to use remote sensing, and it doesn't really matter what platform you're using. The first thing we'll go through all of these individually, but height, resolution, size of the invader, scale of the invasion, that all kind of fits into one category, and we'll talk about that. The canopy structure, the timing that you're utilizing, and weather conditions. And these are all things that are just kind of practical considerations that you have to think about before you're going to try to use remote sensing to detect anything. So we'll start off with the idea of resolution. So I mentioned that, you know, satellites are really high in the air, well, not in the air, high in space, and therefore the resolution is really low. And I want to kind of give you a visualization of that. So this is an example. Both of these are from a UAS where we flew at either 60 meters or 30 meters above the ground. So if we're 60 meters above the ground, we have lower resolution if we're using the same sensor. And this is actually from the image showing that. So you can see we've only got 6 pixels of color but flying at 60 meters. At 30 meters, we have far more pixels of color. That potentially means higher resolution and therefore ability to differentiate one species from another. So this plays into knowing how big your invasive species is that you want to detect, because if it's smaller than your resolution pixel size, then you're not going to likely be able to do it, right? You have to have the proper resolution. That's often associated with flight height, if it's something that you can control, and just considering how all these parameters are going to line up together so that you get imagery that's actually helpful to you. The other thing to think about is coverage and basically canopy structure. So if I'm trying to detect this plant down here, it's going to be very difficult if it tends to be covered in a forest system with a canopy above it. It's not technically impossible because there are ways to collect information through a canopy, such as I mentioned with LiDAR. We could potentially measure both the canopy here and the canopy down here at once. But especially if we're using light information, the electromagnetic spectrum that we can typically see, it's going to be very difficult. So kind of acknowledging that if you're working in a system where there's a canopy above, it becomes a lot more difficult to use this type of information. So the next thing to consider is timing. And this is an example from one of our study sites where we're looking at, and it doesn't matter the details, we're looking at the study site in August and then the exact same area in September of a couple of years ago. Now, by chance, we were interested in picking out this shrub right here. The timing could be really important in that in September, that shrub starts to senesce and starts looking like everything else around it. If we had gotten out there in August, the ability to separate out the shrub from everything else is likely going to be a lot easier because it has a lot different reflection pattern than anything else around it. So identifying when it would be ideal to collect that information based on how that particular species is reflecting could be really important. So this is the most data-y slide that I'm going to show you, but it kind of gets at that point and some work that we were doing. So it's looking at, again, Dalmatian toadflax. So this is a close-up of those flowers. They're actually very kind of pretty snapdragon flowers. And we're looking at the reflectance of Dalmatian toadflax and the surrounding vegetation in May, June, July, and August. And I don't want to get into the details here, but what I do want to say is these little stars indicate different parts of the spectrum. So again, we're going from green to red, and then we have red edge and near infrared. So we can see these with our human eye. We can't see these. And if we went out and collected data in May, we would be able to detect Dalmatian toadflax across the entire spectrum of information that we're collecting, right? So that's good. That's more likely that we're going to separate out Dalmatian toadflax from everything else. If we instead decided to do it in August, the only one part of the spectrum was different and everything else looked pretty similar. So it becomes a lot more difficult for us to separate out Dalmatian toadflax from everything else surrounding it. So instead of making it more difficult on ourselves and trying to force this work in not ideal conditions, why don't we go out in May when we do have ideal conditions? Now, even if we look at that entire visual spectrum of visual light and we reach out into some of those other parts of the electromagnetic spectrum, there are some vegetation that we might not have the ability to separate out. They're just too similar. And in those cases, we could potentially use what's called a delta analysis, where we're looking at 2 time steps in the season, and then based on that information and the change in vegetation, we're able to pick out a specific species. So let me give you an example. So cheatgrass is relatively unique in that in the spring, it tends to be green before anything else in most cases. But there are some other things that are green during this period of time. In the fall, as I mentioned before, during the real-time imagery, cheatgrass or downy brome tends to turn purple. But there are some other things that can be purple around that time of year. However, the likelihood that the species that are similar to cheatgrass in the spring and the species that are similar to it in the fall are the same are pretty slim. So if I can say, hey, what's the change in color reflectance from spring to fall, and measure that and kind of build an image of cheatgrass change in color, I can potentially still separate out cheatgrass from anything else, even if it is impossible to separate it out at a single time step. So the final thing to think about is very practical, but also really important, and that's just your weather conditions. You know, I already mentioned clouds and how they can be important, not only from being a potential obstruction for something like satellite imagery, but they can make the color of an image very different if you're trying to use something like a UAS where you can avoid the clouds can still impact it. Another thing to consider is wind. And in Wyoming, we joke often that it's quite windy here. Not only does that make it difficult for things to fly in general, you know, if you're using a UAS, it's very difficult for them to stay on track in high winds, but it also can affect your imagery. So this doesn't really show it all that well, but this was on a very windy day trying to collect imagery. And what we saw is that all the grasses were kind of blown over from the wind. So there could be a literal physical obstruction, you know, kind of like I referred to with the canopy obstruction, but it also means that things are moving around. And anybody who's ever tried to take a picture of their kid during a sporting event of some type probably has an experience of something like this, where you're trying to get the image to look like this in the bottom, but it looks a little more like this. Well, if you're trying to detect a particular species and the imagery you have is as blurry as this, it's going to be far less likely. So, you know, having still conditions could be beneficial for your detection. Okay, so that's kind of generally covering everything I wanted to cover. I want to give you one example on some things that we're doing and how it might relate to you all in your positions. So hopefully you're all familiar with, and if you aren't, I highly suggest you spend some time learning about weed-free forage and hay, and now gravel. And the short of it is this program is intended to help producers who want to produce weed-free forage or hay. And part of that process is having some type of a coordinator or weed manager come out and confirm prior to harvest that that area is free of weeds. And this is an example here of one of our colleagues who is using a horse as a way of trying to get above the landscape to try to more easily detect weeds in what is potentially thousands of acres of hayfield. My student Chloe that I've already mentioned gave an example of what would happen if you're trying to find weeds in this particular field that she was working in, and it would be very difficult for her at her height to be able to find any weeds. Why can't we use something like remote sensing in these systems to be able to more easily assist the land managers and coordinators to be able to find any weed issues in a field? So could we use something like a UAS real time to have a flight over that field and bring the imagery back, and then with a computer identify where those plants are or not? So this is one example trying to use remote sensing not independently, but in conjunction with current management strategies that might be helpful into the future. Okay, so here was our objectives, was for you to be able to answer these questions by the end of the presentation. So what is remote sensing? Well, hopefully you realize that it's a pretty broad category. We tend to pigeonhole ourselves a little bit in science and management, but it's really just detecting something from afar. What type of information can we collect remotely that's going to be useful? Is going to be generally light, heat, and distance information, at least for right now in current technologies. How do we collect remote sensing data? Well, we have to use some type of a platform, and they can be as large as something like a satellite or as small as something like a UAS. And then how do we use that information? There's all sorts of ways to use it. And I think that's the thing I really want to get across, is that remote sensing isn't just all computer-based. You know, we certainly use technologies to our benefit, but it doesn't all have to be number crunched. We can use the human eye in conjunction with computer imagery to more better detect invasive species on the landscape. Okay, so that is what I have for you. That's kind of the whirlwind. Intend to just introduce you to the idea of remote sensing. Hopefully that stimulated some questions, some thoughts, and if you have any, please send them into the chat. And with that, I will stop talking and let Belle kind of moderate from here.
Thanks, Dan. That was a really in-depth presentation. We do have several questions. I don't think we're going to get to all of them, so I'll do my best to do a cross-section of the ones we have. We'll start with a question from Nathan Bush, who asks, are you converting the raw digital number from the UAS to true reflectance values?
So yes. I mean, there's a lot of nuance that I didn't get into there. If you're going to be doing this in a high precision way, you have to have some type of calibration panels that allow you to know what is truly full reflection of all of the electromagnetic energy at a particular band relative to what's zero, and then you have to relativize that. So it gets a little more complicated, and I've certainly oversimplified it for the sake of this, but in our cases, yes, we would be actually looking at true reflectance and adjusting and correcting for that via some type of a calibration system.
I'm going to interject a question that I'm not seeing here, but I think some people are maybe wondering, and that is, to your knowledge, do you see, or do you know of land managers at any particular scale using the technology in the way that you described? Can you give some examples of how it's been used in the field?
Sure, yeah, and so that question is why I wanted to kind of give you all the breadth of how this can be utilized, because right now I do know of managers who are using things like basically that live view, where you're going out and just using it as an additional set of eyes that can get to places that is difficult for humans to get. I think that's being used right now by different land management agencies. When we get more to the controlled, supervised, and unsupervised imagery that I described later on there, that is still more in the realm of research, frankly, for the most part, and is not being utilized all that much in the world of management. I think partly due to just limitations of computational power and building proper algorithms and using proper techniques to be able to separate one thing from another. So we're on the leading edge of that. But what I don't want to happen is that we fall behind the curve, because there's a lot of interest in this in more agronomic systems where they're a little more controlled and easy, they're literally controlled systems that have planted rows and such. Can we still use that type of information in the more challenging environments of invasive plant and invasive species management?
Great. Lucas Nip asks, are there other options for looking for weeds under forest canopies besides LiDAR? He's in Western Oregon, and in forest canopy situations, there's always going to be that problem of getting past the trees. So any suggestions there?
I don't have a ton. I will say I was actually at a symposium recently where they're showing some of the ability for new drones to do object avoidance, where theoretically you could maybe even fly underneath a canopy without the concern of smashing into all of the trees. However, then you're very limited to the coverage that you can have, because whatever that canopy height is, you have to fly below. And if that's 30, 40 feet, is it really viable? Are you going to cover enough area for that to be useful relative to just having a human out there? It's far more challenging when you're working in that structured canopy environment.
Great. A question here from Rod Walker. Will you be telling us, do you have species that you have been able to produce reliable maps for?
Defining what a reliable map is, we've been able to build imagery sets that reliably separate one species from another at a proper timing in my group. And then in terms of like the general literature, yes, there are lots of successes of utilizing these training sets of what a species looks like at a particular time to separate out. I know it's been done for leafy spurge, cheatgrass. Again, this is going to be totally biased towards my area. There's actually a couple umbels, so things like in the carrot family, that have more of a unique white flower that has been successfully detected. So there are examples, but again, we're definitely on the forefront of it, especially in natural areas.
Great. A couple more questions here. Angela Gupta is more of a comment, but she mentions that they've put a lot of imagery from UAS images on zooniverse.org, and I'm going to type in that URL for anyone who's interested, where it looks like citizen scientists can review and categorize images, and that might be helpful for people looking for help for additional eyes to help do this kind of thing. And she says they're doing it for Oriental bittersweet and Palmer amaranth.
Very cool. I am not familiar with that particular platform or program, but I think that's a neat idea. And crowdsourcing, well, maybe that's not crowdsourcing, but making it available is going to be definitely the way of the future, because as we start to have better imagery of plants and being able to detect them from others, having that training information is going to be really important, and trying not to rework the wheel by sharing that's going to be, in my opinion, the way forward.
Yep. Let's see, one more. There was a question about mosaicing. Was there a particular application you recommended for doing the mosaic?
It really depends. We've been using. So I should have given a little more background. Our intent in our group is to try to use these technologies that would actually potentially in the near-ish future be viable for somebody on the ground doing management. So we're using Pix4D's version of a mosaicing program. I'm not going to say it's the best. Or the worst. It's just one that is broadly available. But again, it's one of those things where what I say right now might not be relevant 6 months from now. We've gone through 3 different platforms for collecting this information in the 2.5 years that I've been working on it, because the technology turns over so quickly. So what works today might be old news tomorrow.
Mhm. Yep. One
But
final,
that's what we use.
yeah, great. One final question related. You mentioned 2 apps. One was called Drone Deploy, and if you could mention what was the other app that you mentioned?
Yeah, so it's Pix4D, and I still, it's escaping me, and I'm pulling out my phone even because it's not on this phone that I use it, but it's the Pix4D's version of it. And if you were to look up their whole ecosystem of software, you would be able to find it relatively easily.
Great. All right. Well, that brings us to the hour. I want to thank everyone again for taking time to be with us today. Thank you, Dan, so much for this really excellent presentation. This really adds to our member resources of webinars that we will post possibly by the end of today, even for members to go back and access this again at any time. So there's our website. Check us out. If you're not a member, please join us today. We rely on the support of our members to support the programming such as this webinar and others. So again, thank you so much. Have a wonderful day, and we'll see you again on the next webinar.